Alrighty, on to rather a new topic, matrix norms. Okay, what we have here is similar to some things we dealt with in the past in terms of vector norms. And there'll be some real overlap between vector norms and matrix norms in some ways, and other ways not so much. So we're going to define several matrix norms, some similar to vector norms, some not so much. These other ideas you'll see pop up in some other settings like functional analysis as well when dealing with linear operators. Like a matrix represents a linear transformation, so I'm not surprised to hear that there's these ideas in other settings of linearity, more general than just vector spaces. We'll use these matrix norms to finally discuss a little bit in terms of convergence of sequences and series of matrices. Can't talk convergence unless I can measure distance. Maybe it can be done with a topology, but let's say we need a measure of distance to discuss convergence. That's a bit of an oversimplification, but we're going to use these norms to give us distances. And when we talk convergence of sequences and series, it'll be with respect to a metric that's induced by these norms. Okay, so consider the vector space R to the n by m of all n by m matrices with real entries. A matrix norm on this vector space, we saw earlier this in fact was a vector space, is a mapping that takes these matrices into the real numbers with the following properties. For any two of the matrices and any scalar A, we have, since the first three of these are similar to what we had for norms of vectors, we have that the norm of every matrix is greater than 0, well, every non-zero matrix, and the norm of the zero matrix is 0. If we take a matrix and multiply it by a scalar A, the norm of that scalar A times matrix A is the absolute value of scalar A times the norm of A, and we have a triangle inequality. So these first three, same thing we had when we dealt with norms of vectors. Something we can do with matrices that we didn't do with vectors is we can multiply them together and get another matrix, say. So an additional property is added called the consistence property. It's sometimes called the submultiplication property as well. But this requires that the norm of the product A times B is less than or equal to the norm of A times the norm of B. A matrix norm is said to be orthogonally invariant if for A and B orthogonally similar matrices, that is, I can write maybe A as Q transpose B times Q, where Q is an orthogonal matrix. So that would be orthogonally similar. We talked extensively about orthogonally diagonalizable, but orthogonally similar was defined, I think, in the previous section. Maybe in the section on orthogonal matrices, but recently. Orthogonally invariant if orthogonally similar matrices have the same matrix norm. So that's a type of matrix norm, one that is orthogonally invariant. Okay. The definition we're about to give of a particular type of norm is a very common one. We got a little potential for confusion because we're going to have norms all over the place. We've actually got three norms in what we're about to define. We've dealt with norms of vectors in the past. I'm going to denote a vector norm with a little subscript of V in what follows, and a matrix norm with a little subscript of M. Strictly speaking, you should be able to tell from the context whether you're dealing with a vector or a matrix, but at least in this next definition, I'm going to delineate between all these different kinds of norms. The matrix norm, so we're defining this on R to the n by m, is defined as the norm of matrix A is the supremum over all non-zero vectors x of the quotient vector norm of AX divided by vector norm of X. All right. I see three norms. The matrix norm we're defining, the norm down here on vector x, and we're taking a times x. A is n by m, so x must be a vector from Rm. So we're using a vector norm on Rm down here. A times x itself will also be a vector, but it'll be a vector in Rn. And so we're using a vector norm in Rn up here. So matrix norm is defined to be this supremum. This is called a matrix norm induced by the vector norm, actually vector norms, on Rn and Rm. For example, they might be the Euclidean norm, in which case we'd get a Euclidean matrix norm. And this is also sometimes called the operator norm. That's terminology you might hear in more general settings, treating it as an operator, treating it as a, you may encounter functionals, and you'll find the norms of functionals in a similar type way. Gentle textbook uses a maximum instead of a supremum here. Supremum, you know, least upper bound. Every set of numbers with an upper bound has a least upper bound. That's the completeness axiom for the real numbers. I can't say maximum unless I know there actually is a maximum, and we don't know there's a maximum. We're taking this thing over all non-zero vectors. Well, how many non-zero vectors are there in what, Rm? A bunch of them. There's infinitely many, and that's a problem. In the short term, we'll resolve it. But Gentle from the beginning says maximum instead of supremum. You can't do that because we're looking at vectors from Rm, and there's an infinite number of them. An infinite set may not have a maximum. It could still have a supremum, but it won't have it won't potentially have a maximum. Certain kinds of sets that are infinite do have maxima, and that's how we'll resolve this. In one of the exercises, I've modified somewhat when I assign it, you're asked to show that the matrix norm really is a norm. So go through and confirm those properties of a norm for this matrix norm. The vector norm and its induced matrix norm satisfy the following two properties. The norm of AX is less than or equal to the norm of A times the norm of X. Okay, very common property. You'll encounter this in analysis classes, I know. Let's dissect it just a little bit though. AX is a vector and X is a vector. So this is a vector norm and this is a vector norm. This, if it'll let me highlight it, is a matrix norm. So we've got two vector norms and a matrix norm. Unless that's a square matrix, we've actually got two different vector norms. Vector norms from two different spaces, Rm and Rn, same. But this is giving us a bound on how big AX can be in norm as compared to the norm of A and the norm of X. And the norm of A is claimed to be the supremum over all unit vectors of the norm of AX. Okay, so what we're dealing with here is the matrix norm defined above. Here, we're dealing with the norm of a vector. X is a vector, so AX is a vector. And down here, we're dealing with a vector norm as well. So we're taking all unit vectors and we're taking the norm of A applied to those unit vectors, giving us a giant collection of vectors. Take a norm, gives us a giant collection of real numbers, and you take the soup over that. How do you know the soup exists? Well, we're in finite dimensions and we're dealing with boundedness. That's a little bit vague. If we were in infinite dimensions, we'd have some legitimate concerns and we'd make some restrictions to ensure that these soups even exist. But having established this second inequality, by the way, these are to be shown in an exercise as well. Now we're in business to resolve this concern over supremum versus maximum. Remember, we had defined the matrix norm as a soup over all non-zero vectors, and we took a quotient here. what's being claimed in that theorem is, well, you can actually restrict your attention to vectors that have been normalized, that have norm 1, then that denominator goes to 1. And that's the claim here. So that matrix norm can be represented in terms of a soup over all unit vectors from Rm. And then taking the soup of the norm of the resulting AX vectors over these unit vectors. Okay, now about the soup and the max thing. In Rm, if we look at all vectors X such that the norm of X equals 1, that is all unit vectors, that'd be the unit ball in m-dimensional Euclidean space, the surface of the unit ball in m-dimensional Euclidean space. That's a compact set. It's a closed and bounded set. We're in finite dimensions. It's a compact set. So being a compact set, and maybe throwing in an observation that norms are continuous mappings. We've got a continuous function on a compact set. Extreme value theorem says a maximum is achieved. Continuous functions on compact sets achieve their maxima and their minima. That's the extreme value theorem from Calculus 1, sort of writ large. In Calculus 1, the extreme value theorem said a continuous function on a closed and bounded interval has a maximum and a minimum. Well, that closed and bounded interval has been replaced with compact sets in your analysis classes. So indeed, we could actually say this, provided we're in Rm, provided we're in finite dimensions, that the norm of A is the maximum over all unit vectors of norm of AX. If you're in infinite dimensions, and we've mentioned this in passing, that's some bad news for you. The unit ball is not a compact set in infinite dimensions. Well, it's a closed set and it's a bounded set, but it's not a compact set. Remember, Heine-Borel theorem doesn't apply in infinite dimensions. Heine-Borel theorem says a set of real numbers is compact if and only if it's closed and bounded. Yeah, that's real numbers. That's one dimension. Maybe you did your analysis in a slightly more general setting, and the Heine-Borel to you is in Rn. Closed and bounded sets and compact sets are the same thing. A set is compact if and only if it's closed and bounded in Rn. Okay, fine, but that's still finite dimensions. I can give you a space, come back and see me in real analysis too. I'll give you a space, this space little L2, it's commonly called, we've mentioned little LP norms in the past, and we're about to see them again. But the space little L2, square summable sequences of real numbers, is an infinite dimensional inner product space. It's an infinite dimensional Hilbert space. Lots of useful stuff happens in little L2, or space isomorphic to it. And the unit ball is not compact in little L2. So Heine-Borel doesn't hold in infinite dimensions. So I do need the soup thing if we're going to do this in infinite dimensions. We're not going to do this in infinite dimensions, but some people are. Commonly, that's the realm of functional analysis. So in functional analysis, we have a little introductory functional analysis class, fundamentals of functional analysis. And I've got some notes posted online for bounded linear operators. What could that possibly have to do with our topic at hand? Well, the linear part. Linear operators map you from one linear space to another. Yeah, matrices do that too. Matrices, the matrix we've been talking about, these n by m matrices will map us from Rn to Rn in a linear way. Yeah, those ideas can be extended to other settings. And it's done so in this functional analysis class, and they talk about operator norms, and they do the same thing we did. They got a soup right there. Other than that, they do have the unit vectors. Actually, this would be the definition of the operator norm in the appropriate setting in these classes. FYI, some bonus education there. Right now, we want to concentrate on matrix norms. Okay, we use the little LP norm on Rn and on Rm back in section 2.1 when P was 2, remember, and summed up the squares of the absolute values the components of a vector, and then you took a square root. Well, don't raise it to the second power, raise it to the p power and take a pth root, still summing. That's how we define the LP norms. P had to be greater than or equal to 1 for that to actually be a norm. But we've dealt with the LP norms in these finite dimensional spaces, and everything's finite dimensional for us. The induced matrix norm is then called the LP matrix norm, would be defined to be the maximum over all unit vectors when measured with an LP norm of the LP norm of AX. Quite strictly speaking, if matrix A isn't square, then we've got here an LP norm on Rm, and here an LP norm on Rn. So strictly speaking, it's different LP norms. It's different spaces. The norms are calculated in the same way, but there's more components maybe in one of those spaces than the other. So that calls for some attention. And a claim, okay? Theorem 3.9.2 says about these LP matrix norms that for n by m matrix A, so the entries are A sub ij, the L1 norm satisfies L1 matrix, induced matrix norm. The L1 matrix norm is the maximum over J of the sum from I equals 1 to n, the absolute value of A sub ij, and so it's called the column sum norm. Okay, well, let's diagnose that. So ignore this part out here, and let's look at the stuff in the set parentheses. Okay, so what we're doing is fixing J inside the set and summing over I. So we're looking at the sum of the absolute value of the entries in the jth column of matrix A. That's why it's called a column sum norm. So we're taking absolute values along the jth column and adding them up from I ranging from 1 to n. So we're getting a sum of absolute values, an L1 norm of the column of the jth column of matrix A. And then we're taking the biggest one of those. Yeah, I can say biggest, I can say maximum, because there's only m of them, so there's a finite number, so there's a biggest. All right, so the L1 norm defined to be this. We'll go through proof and establish that. It's called a column sum norm because we're summing the absolute values of the column entries and then picking the biggest one of those. The L infinity norm, remember the L infinity norm, sometimes called a soup norm, on say Rn was, I would take the absolute value of the components and pick the biggest one of those, and that was the L infinity norm. And here it says that the L infinity norm satisfies the maximum, this time over I, of the sum from j equals 1 to m, absolute value of A sub ij. Okay, this time in the parentheses, it's the j that's varying and the I that's constant. So this time, when j runs from 1 to m, we add up, we're summing the absolute values of the entries in the ith row. This is called a row sum norm. And then we're picking the maximum of those. So you see some sort of dual relationship, maybe transpose, between these L1 norms and these L infinity norms. Here we're choosing maximum column sums. Here we're choosing maximum row sums. I gotta throw the word transpose in there somewhere and get some equality between these. And we will. Okay, let's go through proof of that. Okay, claim is when we take our definition of induced matrix norms based on vector norms, that we get these representations when using L1 norms and L infinity norms respectively. Alrighty, this proof comes from Horn and Johnson's matrix analysis book. I've got a copy from the mid-'80s. There's a newer edition out, a second edition, maybe even a third edition by now. But there's definitely a newer version. But the stuff is correct in this old copy. Let the columns of matrix A be A1 through A sub m, as we often do. Then take that jth column and denote its components as A1j, A2j through A sub nj, as you know, the usual notation we would have within a matrix A with double subscripts. Okay, take X to be from Rm. We need it to be a column vector because we're going to multiply it by matrix A, which is n by m. So just some bookkeeping. distinguishing between row and column vectors. What we get then is X, a vector from Rm, make its L1 norm 1. L1 norm is 1. Okay, so that means you sum up the absolute values and you get 1. We're about to see some of that kind of thing happen. We need to take the L1 norm of A times X and see how big it could be. The maximum over all such vectors X is the L1 matrix norm. This is a vector norm here because A times X is a vector, but you compute the matrix norms by taking a maximum, since we're in finite dimensions, a maximum over all unit vectors X of this quantity here. Okay. How do you find the L1 norm of a matrix? I'm sorry, of a vector? Well, what is this vector? X is a column vector. When you take A times X, you get a linear combination of the columns of A with the components of X's coefficients. So this produces the vector sum, x1a1 plus x2a2 up through x sub m, a sub m. Remember, the A subscripted A's are columns and the subscripted X's are components. That's how we got here. So yeah, that's just a linear combination of the columns of matrix A. We're taking an L1 norm of that vector. Whoops. Okay, we got a triangle inequality for the L1 norm. So we can apply the triangle inequality to get that less than or equal to the sum of the norms of each of the constituent vectors, triangle inequality. All right, remember the X sub i's are scalars, the A sub i's are vectors. We've got a norm of a scalar times a vector. Okay, so in the next slide, we're going to use another property of, matrix norms, and that was, or vector norms, I guess, the norm of a scalar times a vector or matrix. I mean, these vectors are matrices, just of certain dimensions. So I can go ahead and quote matrix norm if you like, or vector norm. That's the absolute value of that scalar times the norm of that vector. So we get these absolute value of X sub i's out front. Now, we're letting I range from 1 to n and taking norms of the columns, A sub I. I'm going to replace this with the column of maximum L1 norm. All right, there's only m of them. One of them's the biggest one. Replace this norm of A sub I each time with the maximum normed column, the maximum, as J ranges from 1 to m, of the L1 norms of the columns. I'm just replacing that with the biggest value. That certainly introduces an inequality of that sort. Okay, now we can bring that maximum outside of the summation. That's in a sense why we did this. Bring the max outside of the summation. You couldn't do that up here. Summing over I, and we had I inside that norm. All right, and then you're left with a sum from I equals 1 to m of the absolute value of the X sub i's. Why that, by definition, is the L1 norm of vector X, where the components are the X sub i's. Take the absolute value, raise it to the first power, sum them up, and take a first root. It's just the sum of the absolute values. All right, so that is the L1 norm of vector X. Remember, we chose vector X to be a unit vector, so we can just drop that. And then we keep this maximum thing. All right, let's express this in terms of components of matrix A. Column J had components, A1J, A2J, up through A sub nj. So how do you find the L1 norm of a vector with those components? Take the absolute value and add up the components, just like we did with the X vector up here. Take the absolute value and sum up the components. Here we've got components ranging from 1 to n. It was a column of matrix A. Matrix A is n by m. So anyhow, we sum from 1 to n. And that's the very definition of the L1 norm for vector. All right, so what we've shown is we took a vector X of L1 norm 1 and for that arbitrary vector x of L1 norm 1, we got the norm, the L1 norm of AX to be less than or equal to this quantity here. We did it for an arbitrary unit vector x. So for any vector x, where we detect the maximum of this quantity over all vectors x of norm 1, they'd all have this same bound. This bound over here is independent of x. Only depends on the entries of matrix A. Okay, so any chance you remember what we're trying to prove? This thing here is the L1 matrix norm of matrix A. We've shown the L1 norm of matrix A is less than or equal to this stuff here. We're trying to prove the L1 matrix norm equals this stuff here. So we've shown this stuff here is an upper bound on the L1 matrix norm of matrix A. Now we need to change that inequality into an equality. All right, so what we're going to do is pick a very special vector x of L1 norm 1, and for that vector x, we're going to see that this quantity, L1 norm of A times special x, actually equals this maximum. And that'll show the norm not only is bounded above by this, but actually attains this value for some vector. And remember, the x vector gets to vary over all vectors of length 1, L1 length 1. Okay. Let K be something between 1 and m, where we're taking the maximum of the norms of the columns, the L1 norms of the columns. Let A sub k be the one that has the maximum norm. All right. Choose x to be E sub k, the k standard basis vector. So that vector is 0, 0, 0, 1 in the kth position and a bunch of zeros. And then let's see what happens when we look at AX for that choice of x. Okay. A times x, that would be A times E sub k. We've taken x to be E sub k. Okay. Here you would think that what we've got is a linear combination of the columns of matrix A, and the coefficients are the components of E sub k. Well, dude, E sub k is a bunch of zeros, except in the kth position where there's a 1, and then a bunch more zeros. So when we do that, take a linear combination of the columns of A with all these zeros and that 1, that's just going to leave you with a kth column of matrix A. So substitution, perform the matrix multiplication, and we get A sub k, the column vector out. We want the L1 norm of A sub k. Well, we chose A sub k to be the column of matrix A of maximum L1 norm. I know they're one of them of the maximum norm, call it k, and then choose the vector x. All right, all this being done independent of anything about matrix A, other than, of course, it has to have a column of maximum L1 norm. It could have several of them. Pick one. Okay. Now we've got the max here. And what is the L1 norm of that jth column? It's the sum from I equals 1 to n of the absolute value of the components. The components of the jth column of A is A sub ij, I ranging from 1 to n. Take the absolute value, sum them up. We showed this maximum is less than or equal to this quantity here. And we just showed that there is a vector x, a unit vector, such that this L1 norm of AX actually equals that maximum. Same thing here we got here. We've got the upper bound for all such x, and there's a particular x where that upper bound is attained. So the maximum over x equals 1 is actually given by that quantity there. So there's the establishing the result for the L1 matrix norm. We claim the L1 matrix norm of the matrix, which is defined like this. That's why we were talking about this the whole time. Actually equals this quantity here. Okay, let's do the same thing for the L infinity norm. And conceptually, it's the same. We'll get an upper bound, and we'll show that upper bound is attained for some unit vector. Okay, let the rows of matrix A, be B1, B1, B2 through B sub n. The B sub i's then have components AI1, AI2 up through A sub IM. Same kind of thing we did previously, except now we're talking rows. Choose yourself a matrix from Rm. Have to be a column matrix, you know, get the products to exist, where the infinity norm of X equals 1. What's that again about infinity norm? Take the absolute value of all these components and pick the biggest one of those. That's the L infinity norm of that vector. So what we're saying is all of the components of X are less than or equal to 1, and at least one of them has absolute value equal to 1. So one of those components is either plus 1 or minus 1. All right. AX, infinity norm of, okay, same thing. We're going to get a bound on it as given here. And what we're trying to show is the infinity norm of matrix A actually equals this. So here we're getting for any X a unit vector with respect to the L infinity norm. AX, L infinity norm of, is less than or equal to this quantity. We're going to choose a special unit vector X on the next slide and show that for that special unit vector X, this L infinity norm actually equals this quantity, this maximum thing, establishing equality as we did in the first one. We'll have then the infinity matrix norm of A equals some maximum formula. All right, AX for this particular, well, this arbitrary vector X, arbitrary except for the fact that we're requiring its L infinity norm to be 1, would be, okay, we're going to do A times X. Think what you're going to get out. It's going to be a vector in Rn. I think that's the correct dimensions. But we're going to do first row of A times column vector X. Second row of A times column vector X. Third row of A times column vector X. First row of A, it's a little confusing, but I use subscripted B's for the rows of A. I've already used subscripted A's for the columns, so I use subscripted B's for lack of a better thing. So we've got first row of A, that'd be B sub 1, times vector X. So we're treating these as matrices, and B sub IX, that's a matrix product. That's a row vector times a column vector. It turns out it's just a 1-by-1 matrix, which we don't distinguish from a scalar. So it's the, when I equals 1 is the first component of this vector. I equals 2, it's a second component. General I, this is the ith component of that vector AX. All right, so we'll take absolute values of it. That's how you calculate L infinity norms. Take absolute values and pick the biggest one. So absolute values, and then the biggest, as I ranges from 1 to n. Oh yeah, this is a row times column thing. Well, that's equivalent to an inner product. That's vector B sub I inner product with vector X. It's got a little problem that B sub I is a row vector and X is a column vector, so I need to transpose one of them. But indeed, this is a dot product, an inner product, right? You're used to seeing transposes on these. There's no transpose. Yeah, you're used to dealing almost exclusively with column vectors as well. And the B's are actually row vectors, rows of matrix A. So that's why there kind of looks like there's a transpose missing. But I need it over here to make sense out of those symbols. Okay, what happens when you perform this inner product? You get the entries in this vector times the corresponding entries in that vector summed up. The entries in B sub I as a vector are AI1, AI2 up through AIN. The entries of X are X1 through X sub M. So we'll get these times these. We'll sum over, say, J, sum over the second subscript on the A's and the only subscript on the X's. So we get the correspondence. So we get a sum from 1 to M of A sub ij times X sub j. Summing over J. We had an absolute value along from the ride. The L infinity norm gave us that. We had this maximum come along for the ride as well. So we've got the maximum of the absolute value of this sum. Here's where we're going, right? This is the goal down here. We're going to pick up an inequality along the way. Absolute value of a sum, why that's less than or equal to the sum of the absolute values. Triangle inequality for real numbers. Good news, everything right here, it's all just numbers. So there's no vectors or matrices in any of this. It's all numbers. It's components of matrices and vectors. So triangle inequality for real numbers with the absolute value. You can write that as this particular type of sum here, just like we did in the last case. I want to replace a piece of this with a maximum. Let's take the x sub j. J ranges from 1 to n. One of those is the biggest. Replace all of the x sub j's with the largest x sub j, absolute value of. So replace all of those with the largest. We get an equality in one slot, maybe more slots than one, but I expect we get some inequalities in there. So that introduces another less than or equal to. Why'd you want to do that? So I can take this outside of the summation. Ultimately, let's see, I guess first, oh, hey, maximum of the absolute value of the components. That's the L infinity norm of this vector. These were components of vector x. So this maximum of the absolute value becomes the L infinity norm of vector x. Now let's take it outside. Okay, so it comes outside. It was constant. And the stuff we're left with, sum from j equals 1 to m of a sub ij, absolute value of. That's what we were looking for. Remember, the L infinity norm of x was chosen to be 1. Drop it. And we've got L infinity norm of ax, where x is a unit vector with respect to the L infinity norm, is less than or equal to this quantity. We're going to do the same thing next. Next, we're going to choose a special unit vector and show that for that particular unit vector, this actually equals that. We've got this quantity based on a vector x, a unit vector. We're ultimately going for an L infinity matrix norm. That's something that happens over all vectors of norm 1. We've shown all vectors satisfy this inequality. We're going to choose a maximum over here. Well, how big can you make it? You can't make it bigger than this thing here. That's what we just established. We can make it equal to it with a clever choice of a unit vector x, just like we did in the previous one. Okay, so we've established that the maximum over all unit vectors with respect to the L infinity norm of ax with respect to the infinity norm is bounded by this thing here. All right, given, say, an n by n m matrix, let's call it A star. It's going to manipulate it a particular way. Let K be such that when we take this maximum thing, it's attained in the kth row of matrix A. What we're doing is summing up absolute values in the ith row and choosing the biggest of those. Well, one of them's the biggest, denoted by this thing here. So I call it the kth one. I'm still stuck with a summing over the j's inside. So I'm saying the kth row is the row of matrix A of maximum L infinity norm. I take it back. I'm saying the kth row is the row of matrix A with maximum sum on the absolute values. Excuse me, that's not it. That's actually an L1 norm. But that maximum occurs for some value of I, call it K, denote it K. All right, then we're going to take as our special unit vector this x star, defined to be the sign of, we're running along the kth row of A and taking the sign of the entries. Sign SGN thing. When you put in a positive number, it spits out a 1. When you put in 0, it gives you a 0. When you put in a negative number, it gives you out a negative 1. That's why I call it a sign function, SIGN function. Okay, now we'll need that to be a row vector because we're going to multiply it by matrix A. Then, if we look at A times this particular vector, so we're taking any old vector A. I kind of wish I didn't have a star on that one. But A times this particular vector X, take an infinity norm, then that's a maximum of, you know, what happens when you do this stuff. We'll have row of A times column vector x star, row of A times column vector x star. We've denoted the rows of A with the B sub i's. So we get a B1 times x star. It's an inner product like it was before. I'm going to do that as I ranges from 1 to n for all rows of matrix A. We get this as an inner product. And here, what happens when you do the inner product? All right. Well, we've chosen x star to be this vector of 1s and 0s. By the way, I should have pointed out, the infinity norm of that vector is 1. Take the absolute values of all of its components and pick the biggest one. Well, they're all 1s, 0s, or negative 1s. One of them has to be non-zero, unless we take A to be the 0 matrix, in which case we don't have much to do. But for A not the 0 matrix, indeed, this is our unit vector with respect to the L infinity norm. So what's happening when you do the dot products down here, the inner products here, is you're simply taking the entries of this ith row, and when they're positive, you're multiplying them by 1 and not changing them. When they're 0, you're multiplying them by 0 and you're not changing them. When they're negative, you're multiplying them by -1 and you're making them positive. And so that's why this was the choice for this vector. In so doing, that introduces absolute values. Here we're looking at the ith row of matrix A. So we get absolute values of A sub I j. The j varies, the I doesn't just yet. It will when we look at the maximum. And so for this particular vector, x star, we're getting ax star, L infinity norm equal to that quantity I keep calling it. We already knew that we had, for any vector x, we had an upper bound of this quantity. We've shown there's a particular vector x of norm 1 where the norm of A infinity actually attains that maximum. Since we're taking a maximum over all unit vectors with respect to the L infinity norm, that being the matrix, the L infinity matrix norm, it has to equal this quantity. We got it as an upper bound, and then we showed the upper bound was attained twice. Now, next, as I commented earlier, we take A to be an n by m matrix. The L infinity norm of A transpose is the same as the L1 norm of A. And one of these we were summing over rows, and the other ones we were summing over columns. Oh, sure. So that's the kind of relationship we get between a matrix and its transpose. If the matrix was symmetric and equaled its transpose, draw the conclusion that the L1 norm, L1 matrix norm, and the L infinity matrix norm are the same. An exercise has you show the following. If we look at the L2 matrix norm, I like L2 a lot. There's a lot of neat geometry in L2, the infinite dimensional vector space. When we use the L2 norm, well, it was just a Euclidean norm when we used it on vectors. The claim here is the L2 matrix norm, one might call it the Euclidean matrix norm, and the spectral radius are related as follows. Matrix A, the L2 norm equals the square root of the spectral radius of A transpose A. Any concerns there? Yeah, I really didn't see this coming. Spectral radius, that's the modulus of the maximum size eigenvalue. So here comes this stuff in a conversation about the eigenvalues of a matrix in connection with these norms. So I don't see that as an intuitive result myself. Spectral radius, not even of matrix A, but of A transpose A. Well, we couldn't talk about spectral radius or eigenvalues unless we had a square matrix. So sure, we got to consider something of the form A transpose A. A may not be square, but A transpose A is square. So there's a claim about a relationship between the L2 matrix norm and the spectral radius of A transpose A. Orthogonal matrices are really well behaved in this. In one of the exercises, it's to be shown that for Q, an orthogonal matrix, remember what orthogonal matrix means. It means the columns are an orthonormal set of vectors. Orthogonal matrix has columns which are orthonormal. They're not called orthonormal matrices. They're still called orthogonal matrices, but their columns are more than orthogonal. They're orthonormal. That's common terminology. Claim is, for an orthogonal matrix Q, Q times vector X, L2 norm of, is the same as the L2 norm of Q. I'm sorry, the L2 norm of X. So multiplying this vector X by an orthogonal matrix doesn't change L2 norms. If we consider this matrix Q as a transformation, say from Rm to Rn, matrices represent linear transformations, then such a transformation is an isometry, same measure is the idea. Links of vectors are the same. If I define transformations, linear transformations, using orthogonal matrices. There's a study of isometric matrices that in general satisfy this kind of relationship. Orthogonal matrices are a special case then of these isometric matrices. If we were to take, using the L2 matrix norm, if we were to take a soup of this divided by the norm, the L2 norm of X, if we were to calculate the L2 matrix norm of Q, we divide both sides by this L2 norm of X. On this side, you get a 1 on the right-hand side. Do your supremums or your maximum things, and you'll see that the L2 matrix norm then of an orthogonal matrix must be 1. More generally, if A and B are orthogonally similar, so that means I could take A and represent it as a, say, a Q transpose BQ, where Q is an orthogonal matrix, then they'd have the same L2 norms. I'd apply this idea a couple of times. I guess it's a consistency property. The norm of the product is less than or equal to the product of the norms for matrices. So yeah, I take it back. We'll need a little bit of that in there. The A and B play a symmetric role in what's set up here. If A is orthogonally similar to B, then B is orthogonally similar to A. So there's a symmetry there that would allow us to deduce this equality. Another norm, the Frobenius norm, is defined as follows. Exotic name. I think that's the common name. I have seen that in other sources. It's also called the Euclidean matrix norm. That brings a smile to my face because they're treating it just the way we would treat vectors in a regular Rn vector space. They're squaring things and taking a square root. The Frobenius norm of matrix A, norm of A with a little f as a subscript, is defined to be the square root of sum over I, sum over j, a sub ij squared. They're summing all the entries squared in this matrix and then taking a square root. Hey, this is a Euclidean matrix, I'm sorry, the Euclidean metric, if you apply it to matrices that are, say, column vectors. So it's the same kind of thing you do in the Euclidean setting. I'm really happy with that name, but I do think Frobenius norm is a common title for this. The Frobenius norm, hey, it satisfies properties 1, 2, and 3 required in the definition of a matrix norm because vectors in R and M satisfy it. You're treating these matrices as if they were vectors. We've done that kind of thing before. If we wanted to really establish this as a norm, so one of the exercises does that, that consistency property would be the only thing left to do. It would be observations we could relate to vectors in Rnm as far as relating to matrices in R n by m matrices. So the computations are exactly the same, but the vectors don't address this consistency property where you multiply matrices together, because you don't multiply vectors together.